So next we have Özge Drama.
Hi everyone, I'm Özge. I'm a PhD student in the Dynamic Locomotion group at Max Planck Institute, Stuttgart, Germany. Today I'm going to talk about the impact of trunk orientation for dynamic bipedal locomotion. So here you see some leg designs from our lab, which are like at the moment monopedally running on a boom, and they are soon to become bipeds and quadrupeds with a trunk, hopefully. So let's start. Let's start with bipedalism. So we see the trunk and the hip. And the challenge here is that we have only one actuator located at the hip, and it has to provide two tasks basically. It has to move the leg, and it has to stabilize and orient the trunk at the same time, which makes things highly decoupled. And if you look at the nature, we are not the only solutions. There are many varieties with different number of leg segments, different of crouchiness of the legs, and different trunk orientations. And today I will be focusing on the trunk posture basically. So what we have in the nature, we start with orthograde postures, which means that you have a vertebrae which is horizontal to your horizontal vertebrae, and a center of mass which is above your hip point. And on the other side, you have the pronograde posture, which is seen in the red heights. Basically, you have a horizontal vertebrae, and your center of mass is located below your hip. It's 90 to 100 degrees, leaning forward. Somewhere between these two morphologies, we have the bipedal lizards and the other birds, such as passerine birds. And since birds are the descendants of their avian theropods, it's interesting to also look at their ancestors. And what we see here is that you have a completely different trunk morphology. And what you see there is that you have your center of mass right below your hip, and the radius between the hip and the center of mass is relatively short in comparison to your birds. And since we are in HMC, I was really compelled to put Hex runner here as a morphology, which is somewhere between the theropods and the retites. But what I'm going to focus on today would be the human and a retite. So I'm using a spring inverted pendulum model with a trunk, and I'm going to look at the running gaits. So here's our model. So you have a trunk with a certain inertia and a center of mass located here, and you have a massless leg with a spring and a damper as optional parameter. And in the model, you have two control inputs. Basically, you can control the leg angle, and you have a hip torque applied on the hip, which is generating this tangential component on the reaction force. So what I want to achieve is that I want to generate gaits with natural pitching oscillations and investigate the function of leg, trunk, and control. So how am I going to do this? I'm going to do a biomechanical analysis basically and look at the differences between the morphologies. As an example, I picked for my simulation the hip torque versus the angle between the trunk and the leg. And what we see in the human is that since it's quite symmetric, you do positive and negative work during your stance phase, which is behaving like an unstable fixed point more or less. But when we switch to bird morphology, we have to actually insert a lot of energy in our system just to hold the trunk leaning and then move the trunk on top of that. So from a modeling perspective, you're injecting a lot of energy, and to find a steady state solutions, you need to somehow handle this extra energy and deplete it out. So here, as an example, I put a damper in it, but I'm also looking at some passive mechanisms on the hip, around the hip to compensate that, and some varied leg stiffness and more so on and so forth. Second of all, I want to look at the robustness against the step-down perturbations. There is the work of Monica-Daly, which shows that the birds are has a larger range of can withstand 40% of step-down perturbations. So it is modeled as a function of the leg, but I really want to investigate if it's whether it's a function of the trunk as well. And as control concepts, it's okay, I'm using a simple pitch feedback, and I'm comparing some concept called a BPP, basically, which says that the hip torque could be modeled as a function of a point which is on the mass. I'm not going to go to the details, it's a big discussion, but what I'm doing is that I'm throwing an optimizer and try to find existence of such a point, and I'm looking at the Guinea file data, whether it exhibits such a behavior at the moment. So here are some preliminary results. So I created a data database for different morphologies and with different radiuses and different trunk setups. And I'm looking at the biomechanical data. For instance, what we are seeing here is the ground reaction force belonging to that retard. Specifically, what we see is that they are left skewed compared to a human. And Christian Hubitschke is showed that we can model this left skewedness with a simple leg damper. But recent studies with Clemente, with experimental studies, showed that this could be also partially a function of the trunk. So I'm trying to analyze those. So once I'm done with my biomechanical analysis, I want to just implement those on the like a robot with a floating trunk, basically, and see if we can regenerate those biomechanical data in our robots. So I thank you for your attention. Any questions? I will welcome.
Hi, how sensitive is this gait to that thigh length? So if you make it so that your hip is much further or shorter to your center of mass, does that change the gait in any meaningful way?
By thigh length, you mean the
the
distance between center of mass and the hip?
Yep.
It is. I mean, the longer that you make it, is becoming harder to find solutions. So you need probably larger damping, which might be unrealistic, or larger hip torques, basically.
Do you know if there's like a theoretical limit, or as long as you have the right control, you can?
I mean, as long as you don't have torque limits on your motor.
Okay.
I would say.
So I'm blanking on the name right now, and maybe somebody can help me out. But I remember there was someone who showed over here.
Yeah. Can you louder, please?
So I'm blanking on the name right now, and maybe someone can help on that. But I remember seeing a result that human walkers, the ground reaction force tends to pass through a point in the upper chest, which they've shown has some sort of stabilizing effect because it's above the center of mass. I was wondering if you're familiar with that result, and if you could comment on how that would relate to the different sort of center of mass and rotation and ground reaction force things
ground
you're showing.
reaction forces pointing to a point which is higher than the center of mass is the virtual pivot point concept, I'm guessing, that you're referring to. I mean, there are a lot of discussions, and there is a hint in the data that, for instance, when I look at the Guinea fowl data that we have, there are some steps which are yielding to such behavior. But it's an ongoing investigation. Basically, there are 2 points. If it's a point or a trajectory or a region of attraction is also not that clear to me yet. So you can try to achieve it from the control side. Basically, say that, okay, I'm going to use another controller to yield such a behavior, for instance. It's an ongoing process.
Thank you.
Since the structures make the hip torque profiles look so different, do you think that there could be an effect on performance? Is one structure maybe better for high speed and another structure better for endurance?
I wouldn't say high speed, but I would be more interested in the reactions to the perturbations. With speed, I would like to try, but I haven't done it yet.
Our next coffee break is not too far off in the future, so maybe we'll keep any more questions for then. Thank you.